So my name is Willy Semmler. I'm a department member of the economics department at the New School and research fellow at the CEPA. This is the Schwarz Center for Economic Policy Analysis. This event is planned by the CEPA and organized. In particular, I want to thank the CEPA staff, Bridget Fischer and Rafaela, and the secret active workers behind the scene who made this possible. And we had several of those events before, but let me say something about this event first. Now, after these climate extremes that you saw recently and around the world, not only Sandy last year, Philippines, flooding in Europe, and also yesterday a new event in Illinois. So we thought we make a discussion here, start a discussion on the climate report of the fifth climate assessment of the UN. And the first report of this is out, and this is basically the science background, so to speak, of climate change. And there's another report that is the climate extreme report. It's about also 500 pages, whereas the first one is 2,000 pages and more. So it's hard to assess for the media, for the public, and for the academics, for the student, what's actually predicted there, or what are the uncertainties, or what will come. So we have tried to assemble here major experts who involved in the discussion there. I will introduce them later, but the three experts here will come later to the podium. I will introduce them. We are also very lucky that by chance also Michael Oppenheimer appeared here, which will give comments after the three speakers have presented their work. Michael was originally also invited, but he said, I'm too busy with the IPCC and I can't come. Now it turned out that he could come, and he's going to make some comments after this. Yeah, so we are very lucky to have really the great experts here now on board. Now, the idea of our workshop conferences and activities here is somewhat to bring together economists and climate experts, or climate scientists, geoscientists, and basically this interaction of very deep knowledge of the reason of climate change, and then what one should do in economics or in politics to prevent CO2 emission, to design mitigation policy like cap and trade or carbon tax or other incentive system, or to phase in renewable energy, or the discussion is then what employment effect will this all have, for this is important for politicians. And then another important question, economic question, is how is the cost shared, so to speak, around the globe. There's a heavy discussion going on. And those things are not done solely by economists. Economists do some cost-benefit analysis, but you've got to know the substance and the research from climate change. That's why we brought these two groups together actually in a number of events now. We had originally started with some cooperation with the ILO on employment effects of climate change policies, started 2009, then we had a conference in 2010 on the economics of climate change, where the major topics were discussed. This was funded by the Stiftung, Thyssen Foundation, and Arlek Walker Foundation, and the Council General of the Federal Republic of Germany. In 2011, September, we had another conference on renewable energy, and can renewable energy fast enough phased in, so to speak, to avoid the huge CO2 emission is as a mitigation policy. We had then also gotten some support of those funders for publishing a big handbook, a big book at Oxford University Press. And what you see on your seat is basically a little bit advertisement of this new book that is coming out from all our activities here. So the new grant that we got was last year from the Thyssen Foundation for 2 years public speaker series on climate change, and we are trying to keep the topic going, so to speak, with the public speakers series. And we had so far 2 speakers. The first one was Mark Jacobson in the spring, no, before last year already, on how to phase in renewable energy. He is one of the most strongest proponents of renewable energy, and renewable energy can be phased in, and it will solve the CO2 emission more quickly. Then we had Arthur Runge-Metzger from the EU Commission, who gave a presentation on the EU climate policy. And the today's event is so around the, so to speak, climate or weather extremes, particularly based on the UN IPCC reports. And we are very happy to have great speakers and participate in the science part of this discussion, namely Peter Schlosser from Columbia, Bob Kopp from Rutgers University, and Wolfram Schlenker from Columbia. And we'll introduce them later. Now I want to give the floor to Teresa Gilarducci. Teresa is there. Teresa is our department chair and also SIPA director, and she will report a little bit on what we are doing here. So please start.
Thanks, Billy. Hi, I'm Teresa Gilarducci. Welcome all of you to the New School and to our department and to our center. I welcome the online audience as well. And we also encourage you to actually tweet during the event to tell the world what's happening. And the hashtag is CC Econ. Is it dot? CC Econ. Hashtag CC Econ. So I always tell my students to put their electronic devices away, but now I'm telling you to bring them up and keep the conversation going. So I want to tell you a little bit about the New School, even if you are a member of our community, and to people out of the New School about what we're doing here in response to climate change risks. We have many programs, curricular programs for our students that are growing in the area of climate change. The Environmental Policy and Sustainable Management program, it's a master's degree program, is at the Milano School. We have 2 undergraduate programs, in the Bachelor of Arts and gives a Bachelor of Science in Environmental Studies. We have a university-wide organization we call C6 on climate change, and this is organized by the Center for Public Scholarship. Just got a lot of money to run a conference in a few months. And we have interdisciplinary initiatives. Stevens Institute for Technology and the New School students in Milano and Parsons came together, got an award for building a solar-powered passive house, and it was awarded by the U.S. Department of Energy and awarded in the solar decathlon competition. We also, as an institution, as a university, have signed on to sustainable initiatives. We don't provide bottled water for our guests. We only provide pitchers of water. It's a small thing, but a complete signal to our devotion. And our nice big building growing up and due to open in a few weeks, our university center is a green building, LEED certified building. Costs a little bit more to build, but we want to signal out our attention and our concern for sustainability. And we at the Schwartz Center for Economic Policy Analysis, which I'm privileged to be the director, has promoted and set out an agenda for exploring curriculum and research on climate change because of Willy Semler, our Professor Semler, who has persistently used his prowess in research to look at the effects, not so much the causes, but the effects of climate change, and to make the Schwartz Center a way for research on climate change that's often uses heterodox methodologies we want to push it out into mainstream discussion and mainstream policy making. So without your work, Vili, we would not be here today and we would not have a persistent activity in this area. So thank you a lot, Vili, and I look forward to the discussion.
Thank you for the nice introduction and the real nice remarks. And I knew I would forget something. This is this hashtag, so for the Twitter user, this is now available. And I think we can start now with our presentation. The idea was that each speaker gives maybe 15, 17 minutes presentation. And the first one will be Peter Schlosser from Columbia University. He is Vinton Professor of Earth and Environmental Sciences at Columbia University. He is also Deputy Director and Director of Research of the Earth Institute, Columbia University. You know, they have a huge research institute on all the issues that we are doing on well, maybe a little bit lower level here, but we can borrow the experts from there. He is got his academic degrees from actually a German university, from Heidelberg, his BS and MAs, and also his PhD in physics from Heidelberg. He is doing research and teaching on the interaction of climate change and water. So ocean, groundwater, continental water, and particular Arctic region, and how water is perturbed or influenced by human or industrial activities. So he published a large number of articles, more than 120, 130 articles in scientific journals, and was editor-in-chief of the Journal of Geophysical Research. He is sharing and co-sharing a number of research committees, commissions, panels on particular climate change in the Arctic, ocean circulation and climate variability, and is also co-chair of 2 Arctic research commissions for the National Science Foundation of the US. So we are very happy to have Peter here, to borrow him from the Earth Institute, because he can highlight better than anybody else probably the science background, so to speak, of the reports, or the recent reports that came out. And this is an important starting point. Later we get to impacts of possible extreme weather events, but we first start with some science reports. So Peter, please come.
So what I decided to do, because this field is so broad and wide, is to focus on one report, which is the AR5. And there, the part of Working Group 1, which is a scientific foundation. And there I chose to focus primarily on the summary for policymakers. I went back into the report, but those of you who know the report, you can easily find yourself at page 2,200 and something, and you're still not quite at the end of it. So it is an immense amount of work that has been brought together by many of our colleagues around the world. So the way I will go through the talk is to provide a little bit of context, and then just a few words about IPCC, and then I will go into the AR5 Working Group 1 scientific basis report and highlight the main results, and then end with an outlook. And I'm confident that the other 2 speakers will go more into issues of impact and extreme events and what we can do about it and what not. So if we are putting climate into the context, I actually like to talk about the climate change challenge rather than the science of it or the economics of it, because all of that is actually by now pretty much interlinked. I mean, we do have, although it's sometimes you don't feel it that much, but there is a change in the public perception with respect to climate change, and I think it is much more accepted now than it was in the past. There are still a lot of people who are skeptical about it, but still, I think there is some movement. Also, I think the attention has shifted towards solutions. In talks, we are now more asked about what can we do about it, rather than are you sure that there is climate change and who is responsible for it. And that puts decision makers, but also academia, into a position where we have to respond, where we have to really ponder what can we do about what we see. Forget about how it was accomplished. If it's anthropogenic or not, the change is there, and somehow we have to respond. And people like Willy and Wolfram and others around here, deal with the economic side of it. There are others who deal with the engineering side of it. There are some who are looking at the adaptation side. This is and then there's of course the decision science side that goes into it. So the problem has gained complexity since we started to look at climate change a few decades ago. And if we want to do a good job at that, we have to really approach it not just from the side of climate change, but this problem is trans-sector by now. It has a lot of impact outside the climate domain, and we need a transdisciplinary approach to do that. We also have to keep in mind, while we are dealing with the climate change and the impact on the planet, that our planet faces multiple pressures, and climate change plays into that, could be seen as, or it could be attributed as one of the causes for specific things, but in general we have to understand that if we are looking at solutions for any of the problems we are facing, we have to do it in the context of a planet under multiple pressures. And IPCC, of course, is dedicated and has been created to look at the scientific, technical, and socio-economic information that underlies this problem and that informs decision making. Another point I want to highlight here in terms of context is time. So this is a pretty oblique here. I'm not sure if I can highlight anything there. Let me see if I can do it with the mouse, but there's a little bit of room. So if you look at this plot here on the upper left, you see here the CO2 concentration over the past 800,000 years. So here is present, and here is 800,000 years ago. And you can see, of course, there was quite a bit of up and down, pretty much related to the glacial interglacial cycles. Lower during glacial periods, higher during interglacial. And it's pretty much bounded by 280 ppm, which was the interglacials, and about 180 during glacials. Then you also see in the middle that the reconstructions of temperature for the same period are highly correlated with the CO2. So, that is an indication that if you are changing the CO2 content, you also most likely will change temperature. And there is still some debate about what came first. Was the timing, is it temperature that precedes CO2, or CO2 that precedes temperature? But it's pretty clear from basic physics that if you increase CO2, which is a greenhouse gas in the atmosphere, that there should be a temperature effect. So if we take that and now go to the right picture here, and again we have about 800,000 years here on the time scale on the left, and you see these wiggles in CO2, which is pretty much this or a similar plot as this one. And then you look at what we did during the past 100 and plus, whatever, 150 years or so, you can see that we really have pushed the limits. Here is the observed level, and here are projected emission levels. These are higher emission scenarios. I would just focus on this part here, and it just shows that we are actually leaving what I consider as two metastable states, two envelopes, an upper one at 280, a lower one at 180, and we have pushed it by now to 394. We shortly exceeded 400 this spring because there is a seasonal effect, and we are pushing pretty hard at doubling the CO2 of interglacials, and that of course should lead to a temperature effect, which I think we are seeing. So what is the problem then? And this is the last slide before I go into the AR5, is that both developed and developing countries are using increasing amounts of primary energy, and most of this energy is actually produced by burning of fossil fuel. That already has led, as we have seen, to significant increases in the atmospheric concentration of CO2, and CO2 is a little bit more than half of the total greenhouse gases in the atmosphere. And future projections point towards a doubling of the CO2 concentration in the atmosphere. I mean, you probably have heard what is a reasonable level that we can have in the atmosphere. There is the 350 limit, there are other limits, but I think the 560 is actually not something that is unreasonable to assume. And according to several projections that are going to a 560 ppm level, that would lead to a global warming in the vicinity of about 2 degrees Celsius. So IPCC, just one quick word about that program for those of you who are not so close to that. It's the Intergovernmental Panel on Climate Change. It was created in 1988 by WMO, the World Meteorological Organization, and the United Nations Environmental Program, UNEP. And the role of IPCC, and that's important to keep in mind, is to assess on a comprehensive, objective, open and transparent basis the scientific, technical and socio-economic information that is relevant to understanding the scientific basis of risk of human-induced climate change and its potential impacts and options for adaptation and mitigation. It's not meant to carry out the research or monitor the climate system. It takes its information from published work and then synthesizes it and summarizes it and puts it into a form that is usable for a wide variety of stakeholders. And there was a series of these assessments with reports. We have reached assessment number 5, which was the final draft, I think, is from June 7, 2013. The release was on September 30, 2013, and it can be found on the IPCC webpage. You can download it there, and there is the full report, but there's also a summary if you don't want to read 2,000 pages that is made for policymakers that has the essence of what is detailed in the report. So just to give you a sense of what we are talking about, so we have I will talk about the physical science basis, which is done by Working Group 1, and here I focus, as I said, about onto the summary for policymakers. You can see that this is, even the editing group is relatively extensive. But here in this picture, you can see that the drafting authors is a large set of. I'm not expecting you to read any of these names, but this is about 30-something people who were the drafting authors, and then there are draft contributing authors, and there are more who have helped to write the text of the individual chapters. So you really have a broad variety of backgrounds, nations, and so on, and that all was used to create this report. Just a few words about things like likelihood and certainty. And what is stated is that in this summary for policymakers, there are certain terms that are used, and they will come up as I'm going through my talk, so I just wanted to get you a little bit familiar with them. So the available evidence is classified into 3 categories: limited, medium, and robust. For the degree of agreement about a certain finding, the report uses low, medium, and high. And then the confidence level is expressed using 5 qualifiers from very low to very high. And now what does that mean? It says there are statements about events that are deemed virtually certain, and that's at a 99 to 100% probability according to the report. Very likely about 90 to 100, likely 66, about 2/3 to 100, and then you have the intermediate one between 33 and 66, and then unlikely. And there are 2 qualifiers below that, very unlikely and exceptionally unlikely, which just sets a different upper bound above 0. So now let's see what we actually find in that report. It does state about the global surface temperature that warming of the climate system is unequivocal. And that is, and it specifies that and says, and since 1950s, many of the observed changes are unprecedented over decades to millennia. So that's a very strong statement. And it is somewhat stronger than what we had in the 2007 fourth report, which says that the understanding of anthropogenic warming and cooling influences on climate has improved since the third assessment report, leading to very high confidence that the global average net effect of human activities since 1750 has been one of warming. So there is a notch, the confidence level went one notch up, but in line with what was already seen in the fourth report. It also states that each of the last 3 decades has been successively warmer at the Earth's surface than any preceding decade since 1850. And that sort of has been, if you look at the lower picture, you sort of see these, the progressive increase of the decadal average. Now, if we are looking at how much did we actually experience, according to this fifth assessment report, the global temperature difference, which is denoted here by delta T, has been 0.85 degrees Celsius, about 1.5 degrees Fahrenheit, over the period 1880 to 2012. And then it states it is virtually certain that globally the troposphere has warmed since the mid-20th century. How does that look if we are, I mean, here you pretty much see a time series. Here's time, and here is the mean average. Here's the average temperature by year. If we are looking at that as a distribution over the globe, then this is from AR5. Here you can see that the 0 is at the transition from the cool colors to the warm colors. So that, as you would expect, it is uneven. Nature is not very smooth. There is variability, but overall, the warm colors really dominate. Here is, for example, an area that cooled a little bit, and then there are areas that are left blank, and these are areas where the database was not as good as in the others. I pulled a plot from the NASA Goddard Institute for Space Studies webpage, just to make one point, and that is that although we have this consistent warming of the globe as a whole, there is actually a gradient towards high latitudes, and particularly towards high northern latitudes. The Arctic warms about 2 to 2.5 times faster than the average of the globe, and that comes out very nicely in that lower plot. Now, if we're looking at precipitation, and that sort of is one thing that actually might lead towards impacts on many fronts, in terms of extremes, floods, droughts, but also in terms of food security, the situation is much tougher to deal with, because projections of precipitation, because clouds are involved, other factors are involved that are not that well known, that's a more difficult task to do. So if you are looking here again, if you take the 0 point as the division between the cool colors here, the bluish colors, and the brownish colors, then here for 1901 to 2010, or 1951 to 2010, let's focus on the right one, 1951 to 2010. You see actually there are areas where it got wetter and areas where it got drier. And here, for example, in the Mediterranean area, there is a drying. There is some drying in the west of the U.S., but then there are also areas where it got wetter. And this is something that, there is more information gathered, more consistency found, but there is still more uncertainty than with the temperature. What about the ocean and its role in the climate system? It states, and that's well known to many of you, that ocean warming dominates the increase in energy stored in the climate system. And that is simply because water, there is a lot of water on the planet, 70% roughly of the surface is ocean. But also the heat capacity of water is much higher than that of air. So it's no surprise that this is the case. And in that figure here, you can see that between 1950 roughly and 2010, the amount of heat that is stored in the ocean is increasing. Then how about the cryosphere? Another example that has been highlighted quite a bit in recent years, and here particularly there are two things that have been highlighted, one probably more than the other. That's the, and what I'm talking about is sea ice. The sea ice cover actually has receded quite a bit over the past, let's say, 50 to 100 years. And if you're looking at this graph here, we have roughly halved I see I have to go a little bit faster here. We have roughly halved the extent of the sea ice cover, and that has a lot of implication also for using the Arctic in terms of shipping and other economic things. Sea level is rising, as everybody has experienced. This is in millimeters, so it's about 20 centimeters that the sea level has risen, and that's more important actually for storm surges because they come on top of the sea level. Then what about the carbon cycle? Well-known Mauna Loa curve, the Keeling curve, still rising at about 2 ppm per year, not abated. That is reflected in the increase of the CO2 in the surface ocean, and that translates directly into a higher acidity of the surface ocean. This is ocean acidification that has been talked about frequently. Radiative forcing, you saw these pictures before. This is CO2, here is methane, and here are other compounds such as nitrous oxide, etc., CFCs. Let's focus on this here. The total anthropogenic radiative forcing relative to 1750 is increasing between 1950, 80, 2011. Understanding climate, there are quite a few statements in there, and I will not go through all of these, I just will pick a few. It says human influence on the climate system is clear, so the report is fairly certain that we are actually having a big impact on that. And just close with this one here on this slide. It is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. I will skip this slide and go to the next one. There are no scenarios as you were used to them in the past reports, the A's and B scenarios. We now have representative concentration pathways, and I just want to give you a sense of what they are. They are now referring to the approximate total radiative forcing in the year 2100 relative to 1750, and so there are 4 scenarios that go from 2.6 watts per meter square to 8.5. And what they do is they were chosen, the lowest one is actually a forcing that peaks and declines, 1 that stabilizes, and 2 that do not peak, that are simply going on. And if you want to relate them to CO2 concentrations at the end of the century, then you have 420 roughly, 540, close to a doubling, 670 and 940. Right now we are at 394, pre-industrial was 280, and as I said, doubling would be 560. Let's skip over that, doesn't want to go that. So just quickly to move towards the end on the projections. Continued emissions of greenhouse gases naturally will lead to further warming, and here are the projections for the individual scenarios. So here is a high emission scenario, here is a low one. This was the RCP 2.6, this the RCP 8.5, the red one. And you can, if we go to sort of the middle one, the 4.5, that would lead to about a 2 degrees centigrade increase, the high one to about a 4 degrees Celsius increase. The sea ice, depending on which scenario you take, disappears in summer in the Arctic faster or slower. Right now we are actually on a fairly fast track. We are a little bit ahead of the model calculations. And the warming, if you sort of look at the distribution on the globe, for the lowest and the highest scenario is somewhere of the order of 2 for this and 4 degrees Celsius on average for this scenario, for the high scenario. sea level projection up to about 80 centimeters, between 40 and 80 centimeters, and that could actually, depending on how non-linear the decay of the ice sheet is, that could still be a little bit low. Now, quick word on extremes. So it states that several new attribution studies have found a detectable anthropogenic influence in the observed increase frequency of warm days and nights and decreased frequency of cold days and nights. And it says it's now very likely that anthropogenic forcing has contributed to the observed changes in the frequency and intensity of daily temperature extremes. It also states it's likely that the human influence has significantly increased the probability of occurrence of heat waves in some locations. Then on other phenomena such as intensification of heavy precipitation, there's medium confidence, there's low confidence in the attribution of changes in tropical cyclones, so hurricanes, typhoons, etc., due to human influence. And there is medium confidence that a reduction in aerosol forcing over the North Atlantic has contributed to, at least in part, to the observed increase in tropical cyclone activity there since the 1970s. Drought actually has been downgraded from AR4 to AR5. It says there is no really strong evidence and it's no longer supported that human activities are a cause for extended droughts. So let's just close with a few perspectives. Human activities are clearly placing pressures on the physical, ecological and socio-economics, also socio-cultural systems of our planet. IPCC's AR5 does confirm continued changes of the climate system, and pretty much due to human activities. The impacts on individual subsystems are highly interconnected. We have to keep that in mind when we're looking at that, and they are coupled in nonlinear fashion, which makes predictions and projections more difficult. The effects of human-induced global change are more and more visible, and some of that is actually in extreme events, but we will hear more from the following speakers. The other thing that we have to simply keep in mind when we are looking at these reports is that we already have committed to climate change for centuries to come, even if we are stopping emissions now. There is quite a bit that we have imposed on the system, and it will play out. And the question is, how much more will we add to it, and how will that then translate into the degree of climate change? So with that, I will close my remarks, and we can move on to the next speaker.
I think we go on with the next speaker, and then we have a discussion at the end.
Who's the next?
Oh yeah. So the next speaker is Bob Kopp. He is climate scientist and Earth historian, geobiologist and energy policy expert at Rutgers University, Department of Earth Planetary Science, and also associate director of the Energy Institute there. He is also a member of the Institute for Marine and Coastal Sciences, and he has also some policy exposure. He served as Science and Technology Policy Fellow in the Department of Energy in the Obama administration still, and in the Office of Policy and International Affairs. His research is on integrated assessment system, but probably he will explain it himself, what that means. So basically, economists and climate scientists try to work with huge simulation models where many aspects are taken into account, particular diverse geological and climate data. And in particular now he is working on, and his talk will be on the local and global impacts of climate change. So we are coming closer to our region now here. And Bob, please start.
So, as Willie was saying, I got my background is in on the physical science side, but I got involved in sort of impacts work. First, as a postdoc with Michael Oppenheimer, and then as I spent 2 years at the Department of Energy as a Science and Technology Policy Fellow in the Office of Policy and International Affairs. And so the way I look at climate change impacts is sort of shaped, as Willie noted, by this field of integrated assessment, which I would be happy to talk about at length. And I think for sort of the Schwartz Center, that would be a good talk, sort of looking at how basically you get natural scientists and economists and social scientists to talk to one another in a consistent modeling framework. I'm actually going to try to provide a somewhat broader overview than just integrated assessment today, and I also hope to talk a little bit about another area that's a major area of research for me at the moment, which is sea level change and coastal climate change impacts. So as Peter was just saying, climate change occurs in a complex web of interconnected systems. This particular complex web of interconnected systems sort of illustrates the framework that underlies integrated assessment modeling and sort of integrated assessment in general. Just how do we think of the climate system and its relationship to between human systems? And there's a lot of factors that matter when we think about how to translate the sort of physical impact projections that Peter was talking about into actual impacts on ecosystems and human beings. And these include things like population and the affluence of populations. In general, wealthier populations might have better adaptive capacity, they have more exposed to be impacted, but they also have better ability to deal with those impacts. And so when you think about this, and you think about climate change impacts, you really do have to think about them in the context not just of concentration pathways like Peter was thinking about, but also in the term of scenarios of socioeconomic progression over the course of centuries. And so Peter's talk focused on Working Group 1. There's another whole report that hasn't come out yet of the IPCC, the Working Group 2 report, that will focus on impacts. And there will be some in that on some new scenarios that have been developed. Not a lot, because the scenario development process sort of lagged behind the this IPCC process, so more of that will be seen in the next round. But when we think about impacts, we really do have to think about the social context, and I'll talk about that in a second. And the other big challenge is something that our former vice president sort of pointed out. When we think about climate change impacts and we're thinking about them in the context of economics or risk analysis, we have to think about not just sort of our best estimate of what's likely to happen, but also the tail events. What's the 1% likely event to happen? Dick Cheney's words, if there's a 1% chance of extreme climate change impacts, we have to treat it as a certainty in terms of our response. Now, some of you might think that's a little bit out of character for our former vice president. Actually, he was talking about Pakistani assistance for an al-Qaeda nuclear weapon. But the idea that tail events matter, that 1% chance matters in decision making, is something that underlies a lot of our climate change decision making. Now, I'm not a meteorologist, right? So my expertise is not necessarily in extreme weather. But when we think about impacts on human systems, we have to understand that a lot of these impacts occur as a result of the interaction between changes in the mean, changes in climate, and natural variability, changes in the weather. So climate is basically the statistics of weather. So you have here one statement: New Jersey is wetter than Arizona. That's a statement about climate. On average, New Jersey is wetter than Arizona. On the other hand, one day it was raining in Arizona, on the right, while it was sunny in New Jersey, as the guy enjoying the shore on the left is pointing out. That's a statement about weather. These are consistent statements, right? There you have natural variability around the means, and just something that sometimes gets confused in the debate. Here are two other statements. Average temperatures, that's a statement about climate, are increasing over time. It sometimes snows during the winter. That's also a statement about climate, right? There's some variability. But saying, there was a big snowstorm in Washington, D.C., therefore the climate is not warming, right? When I was working at DOE, my walk from my home to my work went past the Capitol and the Library of Congress, and there was about a week back in 2010 where there was a big snowstorm, Snowmageddon, and I noticed as I was walking into work, it was actually, I guess, the week after Snowmageddon, because that week we were all out, but in walking past to work, there was this igloo constructed next to the Capitol. And it turns out that this was built by Senator Inhofe from Oklahoma with his grandchildren, and on the igloo next to that, they wrote a sign that said Al Gore's new home. And their point supposedly was the fact that it snowed in the winter meant that climate change wasn't happening, that the planet wasn't warming. Now, put aside the fact that, in fact, having more warmer temperatures means you have more moisture in the air might, in fact, increase the probability of low snowfalls. Now, regardless of whether the climate is warming, right, you still have weather. And so it's the interaction between those changes in the mean and the variability that realize a lot of the impacts associated with climate change. And I think for those of us here in the Northeast, in particular in the New York and New Jersey region, we sort of realized that a bit last year with Hurricane or Superstorm Sandy. This is a picture of the Jersey Shore. This was Mandaluyong before the storm. This is the picture from 2009. Here it was a week after Sandy. All right? And there's a lot of devastation delivered in these relatively rare events. It's hard to estimate the frequency of a Sandy-like storm, whether it's a 1 in 100-year storm or a 1 in 500-year storm. But there's this interaction between climate and weather, and a lot of the damages are going to be delivered by these weather events that may become more intense or occur in a context of higher sea levels, for example, in the case of Sandy, as a result of climate change. In the particular case of Sandy, sea levels over the 20th century, as Peter showed, rose about 20 centimeters as a result of anthropogenic emissions. Here in our region, they rose about an equal amount due to factors not related to climate. But those 20 centimeters, those 8 inches of sea level rise in New York and New Jersey exposed about 70,000 additional people to flooding. All right, so that's an unambiguous impact of climate. There are other effects that we might talk about and the questions that may or may not have related to Sandy or to things like Haiyan and climate. So, point here, when we think about damages or think about impacts of climate change, we have to think about the interactions between variability, which we call the weather, and changes in the mean, the climate. So, briefly, what do the physical models say about this? We heard a lot of this from Peter. This is just looking at some of the temperature projections from those 4 representative concentration profiles. So the x-axis here on this plot on the left goes from 1900 to 2300. The second red bar is 2100. And this second plot is just showing you projections of the increase over the 20th century from these 4 different scenarios. An RCP 8.5, the highest emission scenario, the one that's sort of closest to business as usual, the projection from these models are in the range of about 3 to 7 degrees C of likely warming. So that's in the 90%, or sorry, this is 90% range, so it would be very likely warming. So that translates into about 5 to 13 degrees Fahrenheit above pre-industrial temperatures by 2100. But global averages are nice, but as Tip O'Neill famously said about politics, all climate change is local, and no one lives at the global mean. If we're thinking about climate change impacts, we have to think about how these global changes translate into local changes. This is a figure similar to one of the ones Peter showed. This is looking at sort of average projections across the models that contributed to the IPCC report, the CMIP5 models, of the relationship between local temperature change and global mean temperature change. So this is in units of degrees C local change per degrees C global mean temperature change. And there's a couple of things that point out, that pop out of here. So one, all the continents are on the warm side of the spectrum. The land warms faster than the global mean. And conversely, the oceans are generally on the cooler side of the spectrum. The oceans warm slower than the global mean. Simple physics behind that, there's a lot more heat capacity in the ocean than there is on the land. And the second thing was what Peter also pointed out, this Arctic amplification. The Arctic is warming more than twice as fast as a global mean for a number of reasons, including the change in the reflectivity of the Arctic as a result of loss of sea ice. This is a neat paper, again, based on the CMIP5 model, so these same ones that are contributing to the fifth assessment report. That came out in, I think, either Nature or Science earlier this year. And here what they've gone through is look at what's the range of natural variability at a whole bunch of different sites in the world. And where do projected changes in the scenario exceed that range of natural variability more or less consistently on outgoing years. And so even though the temperature change in the tropics does not exceed that at sort of mid-latitudes, the range of variability in the tropics is less. And so what you see is that a lot of these tropical sites are sort of escaping the realm of natural variability relatively early. This site in Indonesia sort of passes the realm of pre-industrial variability by about 2020. You see Mexico City in 2030. The world as a whole, sort of in this analysis, passes the realm of natural variability around 2050, as do sort of the northeast of the U.S. Now, there's significant uncertainty in this analysis not shown in this figure. These are sort of plus or minus 15 to 20 years. But clear by mid-century, a lot of the planet will be sort of surpassing this range of natural variability. Another way of looking at this sort of localization, there's some good work done here in New York City by the New York City Panel on Climate Change. I'm sure some of the people in the room, I know some of the people in the room were involved. And here's just looking at one of these particular extremes, changes in the temperature extremes. So again, drawing on those same set of models, the CMIP5 models. Here we're looking at days per year above 90 degrees Fahrenheit in the the last 30 years of the 20th century, the 2020s, and the 2050s. And in the last 30 years of the 20th century, we had about 18 days per year above 90 degrees Fahrenheit. The projections for the next decade range from about 24 days per year to about 33 days per year, so about a month above 90 degrees Fahrenheit. And by the 2050s, you're basically in the range of 1 to 2 months per year of temperatures with average temperature above 90 degrees Fahrenheit. This is, I think that's actually highs above 90 degrees Fahrenheit. This bottom plot is showing the converse, sort of the days with lows below freezing. So 1971 to 2000, a little over 2 months per year below freezing, dropping to a little bit less than 2 months in the 1920s, and to about maybe a month and a half or a little more in the 2050s. So just these changes in the mean and interacting with the natural variability. Okay, gotta go quickly. Skip over that. Let me just talk about briefly what list of what the actual impacts are. So going through a whole bunch of different sectors, and I should say I'm teaching a 14-week course on the topic of climate change impacts next term, so this is going to be the 90-second condensation of a whole bunch of this. So one significant impact, food security. I'm not going to talk much because Wolfram will talk about this, but warming and precipitation changes we expect to cause decreases in yields and increases in the variability of the yields, both of which are things that can matter a lot for decision making. The uncertainty carries with it its own cost. In terms of energy infrastructure, well, if we have higher summer temperatures, that's going to push increased demand for electricity. And at the same time, higher water temperatures and reduced runoff can decrease capacity at thermoelectric plants. So that's basically anything that uses steam in its process to generate electricity, so fossil fuels or nuclear power plants. And extreme energy infrastructure is vulnerable to extreme events. I think you've probably all seen this picture, again from Superstorm Sandy last year. And what happens here is that in New Jersey and New York, a lot of the substations are where they are because Thomas Edison, when he was starting building the grid here, thought it would be a good idea to place substations near the demands, which were industry along the coast. And as a result of that decision and the buildup of the grid over the subsequent century that locked those decisions in place, and when you have the storm surge like we had in Sandy, there's significant vulnerability there. Now, if you wanted to go and, say, move some of these substations away from the shore, that's a very significant investment of resources. And that also makes the point that some of the decisions we're making today, Thomas Alva Edison was making these decisions beyond a lot of the time frame of a lot of the models we're looking at. A lot of these figures are ending in 2100. Well, there's more than 100 years in many cases that separate us from some of these infrastructure decisions. So we really do have to be thinking on a longer time scale. There will be health effects. This is this one study looking at allergy impacts. On the left, this is just looking at allergy impacts in the 2020s based on interactions and the changes in ozone pollution as a result of warming. And you're seeing sort of 5 to 10% increase in emergency room visits by children in this particular set of model results. One of my colleagues, or two of my colleagues at Rutgers, Leonard Beerley and Kevin Lyons, had a study out last year projecting about a 30% increase in medical expenses for allergies and asthma as a result of climate change over the next decade, linked to both the ozone effect and to the longer growing season. Coastal flooding, I'd love to talk about this at length because this is something I spend a lot of time working on. This figure is just showing you areas that are submerged in this area with a 10-foot sea level rise and storm surge combination. Right now, 10-foot sea level rise is about a 10-foot storm surge is about a 100-year storm. If you just add on to that 16 inches of sea level rise, that becomes about a 1 in 10-year event. And right now, below 10 feet in New York City, this is from this Climate Central website, which is a great resource. There's about $200 billion of property exposed, over 1 million people, about a third of whom are high social vulnerability, so groups like the poor and the elderly. 464,000 housing units, 75 fire stations, 31 hospitals. And this figure is showing some work that we've done looking at several different sea level rise scenarios. And we looked at a number of plots looking at sort of global sea level rise projections. I skipped through one, and Peter showed one. But when we think about impacts, again, nobody lives at the global mean. So you have to take into account effects like land subsidence, like ocean dynamics, like changes in the gravitational field of the Earth resulting from ice sheet melt that cause local sea level changes to differ from global mean sea level changes. So this big bar on the left is showing you a range of historic flooding levels. So this is a 10-year storm here with about an 8.5 feet flood level at the Battery. This is a 1 in 100-year storm, a little less than 10 feet. This is Hurricane Sandy, 14 feet at the Battery. But if you add to that 16 inches of sea level rise, which is sort of a medium projection for 2050, you see that 1 in 10-year storm, that red line, and now surpasses the 1 in 100-year level. If you go up to 66 inches of sea level rise locally, which corresponds to a bit less than that globally, and maybe is about a 3% probability event, you see this 1 in 10-year storm surpassing the storm tide of Hurricane Sandy. Another impact I just want to flag, because I obviously don't have time, I'm out of time, so I don't have time to talk about this, but this will have ecosystem impacts as well. It's not just on people. This figure is from that same study I showed you earlier, showing when hotspots of ecological diversity pass outside their realm of natural variability. And so you can see like coral reefs starting about 2035, plus or minus 10 years, sort of pass beyond the realm of historically experienced conditions, and so forth for some of these other biodiversity hotspots. As I already mentioned on the first slide, impacts occur in the context of social vulnerability. For example, wealthier societies are better able to cope with tropical storms. This is a figure from some work that Bob Mendelsohn and Kerry Manuel and England and some others did last year, looking at tropical cyclone projections and the damages they caused. These are in percentage of GDP. And even though North America is not that much less exposed to North Atlantic cyclones than Central America and the Caribbean, the damage as a percent of GDP to North America is significantly less. Empirically, damages as a percent of GDP from tropical cyclones go down with income. And interestingly, they also seem to go down with population density, perhaps some sort of hardening effect. When you put more people together, you invest more in protecting them. And sort of one example, this is from the shore in Jersey. Right? It costs a lot of money to raise your houses like this, but we as a society can afford to do that. Not all societies can. And yet, even though we can, we have the capacity to adapt, a lot of economic modeling sort of assumes that adaptation is going to happen in an optimal, perfectly rational fashion. We also can just look around and see that's not the case. I don't know how many of you heard about this particular case, but there was a couple in Harvey Cedars that sued the town of Harvey Cedars early in 2012 because the town had built a dune and it diminished their view, and so they sued the town and were awarded $375,000 of damages. After Sandy, they continued their suit, but the town appealed, and the Supreme Court over the summer ruled, well, the benefit they got from still having a home sort of counted towards that, and they reduced their award to $1. But point I want to make there is just adaptation isn't optimal, but it is important when we're thinking about how we translate these physical changes into impacts. And understanding what the costs of climate change are really requires understanding of the dynamics of the social systems. Two other points. One area that I think has not been looked at in general very well from sort of an economic or social effect system is the effect of possible sort of tipping points in the Earth system. Many of you have probably heard about these, but things like positive feedbacks in the West Antarctic ice sheet leading to significantly faster than expected ice sheet loss, or the significant change in Atlantic circulation, or die-off of the Amazon rainforest. There's not much literature on what the actual economic consequences of these sorts of events would be, nor is there much literature on some of the sort of human tipping points that might be result from stacking of physical impacts on one another. And finally, going to end with, I think, what the same bullet point that Peter ended on, right? The world does not end in 2100. Climate change doesn't stop in 2100. And if you look at some of these later effects of business as usual scenarios like RCP 8.5, some of these might be extreme. This is a figure from Matt Huber's group. So here they looked at what a world would look like with 11 degrees of warming, and they're looking at a parameter called wet bulb temperature, which basically measures the combined effect of heat and humidity. And right now, there's nowhere on the Earth where that wet bulb temperature exceeds at any time during the year about 35 degrees Celsius. In fact, it's a significantly lower than that. But this map is showing you with this 11 degrees of warming, which is something that under RCP 8.5 has about a 5% probability in 2200, areas where you exceed about 35 degrees C. Now 37 degrees C is body temperature, so if you're generating heat and the wet bulb temperature is above that level, you aren't able to cool yourself by sweating. So this is a very deadly situation if you don't have air conditioning, if your air conditioning malfunctions. And you can see these areas in purple, eastern half of the US, a lot of India, a lot of China, with which you start to see these sort of very high wet bulb temperatures with 11 degrees warming. So, right, so this is, if you were on this trajectory, that could significantly reshape essentially the geographic boundaries of the United States. So I'll just leave you with this picture of Hoboken during Sandy as a memoir. And just turn it over to the next speaker.
Thank you very much. Then the details on our region here we can expect. The next speaker is Wolfram Schlenker. He's also a professor at Columbia University, School of International and Public Affairs, and is also a member of the Earth Institute. He's a research associate at the National Bureau of Economic Research, and got part of his academic education also in Germany at the University of Karlsruhe, engineering and management science, and then a degree from Duke University on environmental management. And in particular, he has his PhD from University of California, Berkeley, on agriculture and resource economics. And this is actually his expertise, and particularly the impact of climate change on agriculture, food production, rural areas, and so more, I guess, the impact on our developing economies. And he is a very important economic analyst of this, and I have used many of his papers in my classes. I also must say that I'm grateful that he came, because he just comes from Hawaii giving a talk there, and he must be very, very tired. But I'm grateful that he made it today. So please start.
So I want to sort of give you the kind of studies I've mainly done is mainly statistical studies. Do you have the quick one? Oh, yeah. The studies I've mainly done is statistical studies, so I want to give you a motivation for what I've done them, why we're doing them, giving you sort of start with the US, because the US we have much better data, and then we our result is usually that the extreme temperatures is what drives everything, so I guess that's how it fits in this conference, more so than water availability, and then we're going to try to shift to Africa, time permitting, and global production trends. So there is sort of some of the speakers here basically, Rob worked on both process models and statistical studies, but the idea behind process models is that they're very intricate models, that they'll have lots of variables, like how much fertilizer you apply on every single day to a plant, what the soil moisture is, and everything else. What we've done, on the other hand, is sort of much more reduced form. We're looking for some key variable that sort of explain in a large scale what's going on to yields on national or global levels. So Cynthia Rosenzweig, who's a crop modeler, compared this to the Moneyball approach. I don't know whether you saw that movie. I like that a lot, because for the first time ever I can come home and tell my wife, hey, today somebody compared me to Brad Pitt. then we saw the movie, and I realized that the guy who actually runs the regression is Jonah Hill, so it didn't go over so well in the end. But so the kind of stuff we're doing is sort of running statistical analysis. What we've usually found is that the key driver is this concept of degree days, which is a measure of heat that accumulates over the season. So what we're basically doing in a gist is we have minimum and maximum temperature on a really small scale grid for the United States. And there's sort of papers that is roughly follows a sinodal curve between minimum and maximum. And then if you're worried about a certain bound, like our bound that we found, I'm going to show you in a second, is 29 degrees Celsius or 84 degrees Fahrenheit for corn, then you basically take the difference to the bound, which is basically the area under it, and you undercrate under it. So basically what that means is that if you're 10 degrees above the threshold for 1 day, it's equivalent to being 1 degree above the threshold for 10 days. Because, it's just how much you're above it and for how long, and that's basically what adds up over the season. So that single measure explains about half of the variation in year-to-year corn yields in the United States. So it's one of the best predictors. And the 2012 drought you could predict very easily with this, and so forth. So going then into what we've done for the United States. So this is a data set we constructed which sort of keeps very fine-scaled track of what's going on. It's on a 2.5 by 2.5 mile grid. I should mention that there are sort of different identifications I'm going to talk about in a second. It sort of very much follows up on what Rob said. We're going to start by sort of looking at weather events, but I'm going to try to convince you that what the results we're getting for a weather event is actually the same as what we're getting for a climate event. Noticing that the two are different because one is sort of random year-to-year shocks, while others are sort of supposedly shifts in mean over time. So we have this now extended to 2013, and so we basically then link this to the areas where corn is grown and basically what the yield is on a county level. And what comes out of this model, so here on the left you see corn, on the right you see soybeans, is sort of this intuitive fact that you see three different models. One is sort of allows for dummy variables, which is like a step function. One is continuous by design. The other one is sort of forced to be piecewise linear. But they sort of all agree with this basic notion that warmer temperatures are good up to a point when they become detrimental. So if you were able to, and here at the bottom you see the histogram of the historic distribution of those temperatures. So that's quite a bit above this threshold. So basically, if you increase temperatures from the lower range and bring them higher up to 29, that actually improves crop yields. But if you take anything from 29 or close around this and push that even further, it significantly decreases crop yields. Now, the important thing to note here is that the slope of the decline is about 10 times as steep as the slope of the incline. So if you shift that whole probability mass rightward, you get a little bit of a beneficial effect because you make something sort of more moderate that are cold, similar to the less freezing days we've just seen. And at the same time, though, you put a lot of the stuff that's currently moderate and make it really hot, and that has very detrimental effects on yields. And sort of that effect sort of is what, in our statistical analysis, pretty much drives everything. And we find something very similar for soybeans. So that's sort of the gist of the key extreme measure that we then summing over our season, and that sort of seems to predict yields very well. Now that is basically, the previous slide was done using sort of year-to-year variation. So you basically compare yields in a county in 1 year to the next year compared to how the weather deviates from their mean from 1 year to the other. So that's weather fluctuations. However, what we can do here is, which is sort of what's called a cross-section, we can also just compare the average amount of heat that a county has on average. Like, for example, in Iowa it's less than it's down in Mississippi, and the average yield that you get. And linking those together is basically done here in red. If you do a time series, it just looks at the US aggregate yield, and the panel basically looks at all those 2,000 counties for 56 years. And sort of the driving thing here that seems sort of surprising to us is that they all give you pretty much the same result. It was surprising because, as has been previously mentioned in a lot of the other socioeconomic spectrum, we basically find that with adaptation, we find in the cross-section less of a relationship than we find in the year-to-year. But this sort of suggests that actually breeding against this extreme heat is very, very difficult. And that's maybe why we haven't made so much progress in it. So these are sort of some numbers that just, you can pick sort of your own uniform scenario over the Corn Belt. So different climate models has been emphasized in the previous talk, sort of lie in between those different ones. But you see that fairly rapidly, because of this nonlinearity, you get very, very significant negative impacts. So yields are quite substantially decreasing. So what this basically, so since this weather variable, this degree of 29 is sort of the key driver, what this graph does is it just plots it over the season. So day 0 is basically April 1st here, and then it's 183 until the end of September. And then for each day, you look at the average over the whole United States, which is averaged over the corn growing area. And this is basically cumulative. So each day you observe another degree day. This graph just ticks one thing up. So you see here that 2012 was very hot. Only 1988 was hotter. It received a lot of attention last year, partly because a lot of the heat, as you see, happened in July, which is during flowering, which is sort of when heat supposedly is most damaging. Now 2013 actually is even hotter. On the other hand, though, in July it wasn't that hot, which is sort of the flowering period. You see that the difference between the end of July to the beginning, it doesn't raise up as quickly as before. But here again, you see that sort of 2 of the last years are sort of really on the upper one. All those gray lines here are basically the historic ones from 1950 to 2011. So those 60 years before. On the other hand, whenever it's very, very hot, it usually is also very, very dry. So what you see here is this is actually 2012. It's the second driest year. Again, 1988 was only the drier one. This is the weather measure over the Corn Belt, so it's not the whole United States. Now, 2013 was a really weird year because it was hot, very hot, and it was also very, very wet. So it's actually curious to see what's going to come out of this with corn yields, because usually when it's very, very dry, very, very hot, it's also very, very dry. So that's going to allow us to refine the models a little bit more to see whether more precipitation can actually counterbalance some of the damaging effects of heat. Another study that's basically by Berkey and Emmerich that is very, very nice, doesn't look sort of at year-to-year weather variation. What it basically utilizes what also Peter showed you at the beginning. There's observed trends. So this is basically between 1980 and 2005, and you realize that then some areas over the Corn Belt have gotten hotter, while other areas over the Corn Belt have gotten colder. And they basically compare the trends over 25 years in temperatures to trends in basically corn yields. And what they then find, if they look at a coefficient on degree days, basically they find exactly the same coefficient that we've previously sort of identified. So again, this is sort of the closest that we get to climate change, because here a farmer really notices that, whoa, it's getting warmer and warmer and warmer, and supposedly we could pick up whether they adapt and whether they get better at dealing with it, but it doesn't seem to be the case. The coefficient sort of seems to stay the same, sort of almost suggesting that this is sort of a biological limit. Monsanto is adamant that they're going to be good and they're going to breed better crops that are going to be much better at withstanding that. What sort of gave us a little bit of a cautionary tale is that 2012 basically fits the model perfectly. So the idea is if the crops would have been better by now in 2012, we should have seen much less damages in last year than we actually observed. But if you just look at the prediction of the model and what happened to yields, they actually pretty much overlap. So that's sort of a bit disconcerting. So I mentioned that for us, temperature always comes out much more significant than water. So this is sort of, again, this slope here, this downward slope of the extreme heat. So there's a couple of crop scientists and some of our statistical. So David LaBelle does a lot of statistical metal too. Graham Hammer is a crop scientist in Australia. So we basically compared something where we basically looked at this extreme heat measure, and then we also ran those variables through one of those crop models, which are more process-based. And the interesting thing, because if you go to some of the modeler groups, they sort of say it's not driven by heat, it's not driven by heat, is that they actually observe something very similar. So my non-scientific, I'm an economist, so my non-scientific intuition for that is that I think a drought is a very relative concept. So the idea is when temperatures go up, you need more water. So I don't know, I'm sure all of you ran the New York Marathon at the beginning of the month, but if you like to run, Chicago has a marathon in October every year. So in 2007, I don't know whether you remember it was this really, really hot weather, and in 2007 they ran out of Gatorade. So it's not because they had less Gatorade in 2007 that they ran out of Gatorade. They ran out of Gatorade because people were gulping it down like crazy. Turns out it's not that different for a crop. If it gets hotter and hotter, the water requirements go up very, very rapidly. So a lot of times you see a wilted plant and you say, yeah, that's due to a lack of water. That's correct, because it has less water than it needed given the temperature that we observed. But we do have regions, for example, in the southwest, where total precipitation has remained constant, but temperatures have gone up, and as a result, drought conditions have gone up. So I think there's sometimes this misconception that a drought is only caused by a shortfall of precipitation, but it can also be actually caused by an increase in temperatures. So what we find here is basically that there's this double whammy of extreme heat, that basically you reduce the soil moisture, which is basically the water availability to the plant, but you also increase the demand for water by the plant to basically keep up the carbon uptake. On the other hand, precipitation only impacts the soil moisture, so it's only one. One impacts demand and supply, the other one only basically impacts supply, so that's why we think there's this much stronger effect on temperature. And those temperatures, as you've seen from the previous two slide presentations, are sort of predicted to really go up quite significantly. So this is then what you see, sort of the green one is basically the statistical model, and the black one is sort of the observation that come out of this processed model, and the slope here again sort of overlays pretty much. So moving on quickly to Africa. So Africa is already hotter, but as you already was mentioned in the previous, it's so nice here to be the last one because I can feed on all the previous talks. While Africa is hotter to begin with, the predicted increases are actually lower. So you have that, on the one hand, they're going to be, if you believe it's all in the extreme heat, since they start with a higher baseline, they're going to be impacted more. But then there's a little bit less of an increase, so that sort of brings it down a little bit. But there's this really nice paper by a couple of Bensingers. Basically, they did a lot of field trials in Africa, specifically looking at drought resistance. And they did a statistical analysis where here you see the circles are basically the location of the field plots. You see the crosses are basically the weather sites they match this with. And then what they see is this is basically this coefficient on the negative slope, the decline. This is the positive coefficient on the incline that I showed you before in those graphs. And the only thing that they have different here is because they specifically bred for drought tolerance, is that when it's under drought condition, you see that the effect is even magnified. So what they then did is they basically give you the percent impact for 1 degree warming, and you see for the optimal management, sort of the beneficial effect of shifting some of the moderate, the cold temperatures to the moderate, outweigh some of the damaging effects up until you hit sort of 21 degrees Celsius. But when your average temperatures is higher than that, you suddenly become much more susceptible to warming. Now, if you're in drought condition, that sort of starts already way earlier. But these are pretty significant impacts you can get for 1 degree warming already. So this is just spatially plotting this over time. So one thing I want to emphasize here, again, this is sort of all different kinds of models, 4 different models for different commodities all over Africa, is that it seems that the impacts are mainly due to the temperature and not to the precipitation, which is shown in blue. The temperature is shown in red. That's sort of intuitive. The other thing also, since this is economists and climate scientists, one thing we did here is we sort of, there's uncertainty about what the climate will be, and there's uncertainty what the model parameters are from the economic model. So what we did here is, for basically model uncertainty, we kept the climate fixed at the average and just bootstrapped over the uncertainty from the economic model. For the climate uncertainty, we basically used the point estimate from the economic model as certain and looped over the climate uncertainty. And if you look at those uncertainty bars, you actually realize that they are roughly equal between climate uncertainty and model uncertainty. So we both need to sort of narrow down possibly with the range of how much it will warm, and we should narrow down sort of those economic parameters. They sort of right now, you get the same benefit from making advances in either one of those fields. So let me finish then with sort of, do we already observe climate change, and does it have an effect on global food prices? So this is sort of a model where we just look at the trends that we had in weather over the last 28 years and what the effects are on commodity prices. So there's this paper in Science that I found pretty striking, is that there's sort of phase 4 basic commodities, maize, rice, soybeans, and wheat, that account for 75% of the calories that the population globally consumes. So that's direct consumption as well as indirect consumption, because, for example, maize is often fed to livestock, and then you end up consuming the meat. And what's interesting is, of those 75% by those 4 commodities, the United States produces 23%. So a lot of people think Saudi Arabia is really big in oil. Saudi Arabia's share in oil production is about 8%. So the US share in caloric production is about 3 times as big as Saudi Arabia's share in oil. So anything that goes on in the United States has basically huge ramification for the whole world and commodity prices. And so, for example, the ethanol mandate that was instituted, which diverts about 5% of those calories into ethanol globally, is a very significant driver of global food prices. So what we've done, this basically just shows you over time how this has been trending up. All we do is we look at the global output of those commodities, and then we convert them into units that are more measurable, which is basically the number of people you could feed if they were to consume 2,000 calories per day. So you just convert the number of maize bushels into how much calories you can produce with them. You obviously don't want to just eat maize, but it sort of shows you how it's been upward trending. And the interesting thing here, going back to the ethanol mandate, is you see that this is sort of globally the aggregate shock that we've observed. The largest shock we've observed was a minus 5% shortfall of global aggregate production. Now, the US ethanol mandate actually diverts every single year 5% of production into ethanol, which is pretty much equivalent to the worst shock that we've observed for 60 years. So it's just a huge amount that's basically being done. Here you see those climate trends. We've seen them before. These are relative to the standard deviation. You see that the US hasn't warmed so much, but Europe has warmed quite significantly. This is over the areas where crop is grown. So we sort of contrast the more recent past to the real recent past. So when we start out with 1960 to 1980, what you basically do is you look at country and crop-specific trends that you fit for each commodity in country, and then you look at the histogram. And then you do a placebo in gray, which is basically telling you just use an IID process and you look at the distribution. So you're going to get some positive trends by chance, you're going to get some negative trends by trend, and you're going to see that those two basically completely overlap. Now fast forward from 1980 to 2005, and now you see that there's this huge number of positive trends that things have gotten warmer, while the placebo again is sort of centered around zero. So suddenly we've sort of this last 3 decades, we've really experienced this increase in temperature. As a result, this is sort of the estimate of the production losses you already observed. Now we can add in some CO2 fertilization, which is sort of a bit controversial, but if you want to give it the benefit of the doubt, it basically implies that the trends that we already observed, sort of, if you don't factor in the CO2 fertilization, gives you about a 19% increase in commodity prices. If you give a very generous CO2 fertilization, it's about 6.4%. So we're already observing this. It already has an impact on food prices. It doesn't really impact people in the United States too much because the raw commodity costs are a very small fraction of what you pay in the supermarket. But it does impact people a lot if you're in developing countries where people sort of live on subsistence levels. So to conclude, I wanted to focus on one particular aspect here, which is basically this extreme heat, since this is sort of the idea of this conference. And this is a very, very good predictor of what's going on with corn yields and soybean yields. The same actually is true for cotton yields too. It seems that this measure of how much you're exposed to extreme heat is the single best predictor of year-to-year variation in yields. Now with climate change, that's really predicted to go up. And Africa is already hotter, so they're actually predicted to even impact more. So I'm looking forward to Michael's comments on everything I missed.
Thank you very much. And so we are very lucky to have Michael Oppenheimer here too. He originally wanted to participate in this discussion, and he was so busy with the IPCC report, the last one, that was discussed today. And it would be a pity not to let him speak about what the previous speakers have mentioned here. So, and I also know that he was immediately mentioned in the German Spiegel, Michael Oppenheimer, when this report came out, because he had to respond to accusation of more conservative climate researchers saying, well, your range of variations there is much too high and it's much too pessimistic, and Michael responded to this. So please let us know what you think.
I'll be brief. This is off the cuff. I just walked in to enjoy myself, and I got drafted. Very good presentations. I just want to mention one thing from each of them that grabbed my attention. And Peter's, the thing you should pay attention to is that graph that showed that regardless of emission scenario, the results or the outcomes for the next 40 years or so are the same. So we are stuck with the climate change that's built into the system for about the next 40 years, no matter what we do on the emissions reduction front within reason. And by the way, it's a premise of mine always that in order to grapple with this problem at all, we need to reduce emissions rather sharply and rather quickly, because there'll always be a gap between our ability to adapt to the changes and the speed at which the changes are coming. And you can't close that gap just with adaptation. Bob made that point effectively by saying that, look, there's a lot going on here. It's going to impact us locally in many different ways, and we really have to start not focusing away from emissions reduction, but that adaptation is an absolute key. It's, in fact, it's a moral imperative. We can't just sit in rooms like this and think about, gee whiz, the governments will get this under control eventually, because it's already too late for that. We may, in the long term, get it under control in the sense of having an outcome which is better than what would have happened had we done nothing about emissions. But at this point, we have to think about adaptation seriously as something we really have to focus on as well. And then Wolfram made the interesting point that in some sense, in sectors of the problem, I hope not in the problem as a whole, we may be running up against limits of adaptation. Certainly in the crop area, that looks like it's a potential outcome. And actually, Bob made the point, too, with regard to human health. If things get out of control, there are limits to this thing in terms of what we can do to deal with it. So we tend to think of ourselves, and there are optimists in the world that think that human beings essentially can eventually, you know, maybe with some damages, but we can deal with things. We can engineer our way out of situations. Maybe we will genetically modify corn in a way which will allow us to recover. But the truth is that there are changes occurring on such a wide sweep of the human experience, and that will have impacts across such a wide sweep that and affect everyone, that it would be unwise to expect that we're going to be able to engineer ourselves out of a hole across all that whole range of human experience. So that brings me back to the extremes, and looking at that gap as it now exists between the climate changes and our ability to adapt. Let's just forget about climate change. We do a lousy job today in adjusting to climate extremes. When we have warnings of these things, which in the case of, say, Hurricane Sandy, where we had nice level of remarkably good forecasts, there's just a limit to what we're able to do. We cannot marshal our resources quickly enough, nor overcome the embeddedness of the system, for instance, as you pointed out, the Edison problem, so to speak, in a manner which allows us to adjust effectively. So, for instance, even in a very highly developed, rich area like New York, people died in the dozens due to Sandy, and I can tell you they didn't have to, that a more effectively organized emergency response would have prevented almost all of those deaths. I'm willing to speculate within an order that was an order of magnitude too high. In Europe in 2003, from a devastating heat wave, again, it has been associated with climate change. You can do a level of attribution to climate change and show how the probability of the event increased as a result of climate change or the buildup of the greenhouse gases. About 40,000 people died. That didn't have to happen either. Surely some people would have died in that heat wave. It was gargantuan. But the death rates were probably an order of magnitude higher than they needed to be. And probably the same thing is happening right now in the Philippines, where more people died than needed to happen if there had been a cogent system and good governance in place. So, the lesson and on the flip side of that, there are some countries which actually in some ways, even though they're poorer than us, do a better job on parts of this problem. The classic case is Bangladesh. There are tropical cyclones that rip up the Bay of Bengal every year, smash into the coast. The whole place is virtually at sea level, and people drown, and they drown in big numbers. And in 1970, the same year in which there was a civil war in what was then East Pakistan, about 1 million people died in a cyclone. We don't really know how many. And that because of those kinds of episodes, the government eventually learned. The governance situation got better in Bangladesh. The country got a little less marginal economically. And what do now? They do the simple things. They installed an early warning system. Cheap, easy. They started building concrete bunkers. Again, not expensive at all. And now the death rates, although they're still too high, are in the thousands instead of hundreds of thousands to 1 million. The country next door, Myanmar, which until recently and actually still has not had a very appealing governance situation, the same kind of cyclones still kill in the tens to nearly 100,000. So the lesson there is, number one, even in rich countries like Western Europe in 2003, countries do a lousy job with the current level of risk, and the risk is increasing due to many of these features. Number two, it's not all hopeless, at least in the next few decades of risk change, because we know human beings aren't stupid and they do eventually learn there are things that can be done. But number three, if emissions keep increasing, you can throw that bet out the window, because I don't believe that we can really keep up with the changes.
Thank you very much. So this was a wonderful session. I think with all the presenters and the wonderful comments at the end. I must say Michael is Oppenheimer was a professor at Princeton University at Woodrow Wilson School, all right? Woodrow Wilson, and trained in physics as well. So we have a good expertise here on this side. So I think we can start now discussions. We have a little bit time, so if we can more than 1 hour, 1.5 hours. So if you are patient, we can now start discussion. So we had a microphone somewhere. Oh yeah, it's right there. So who wants to ask questions? Oh, there, this lady.
Mr. Schlosser, you never mentioned methane, and then you pointed the map of the tremendous changes in warming in the northern area of the world, and the tundra, and the methane that might seep through global warming. I was wondering if you could mention the impact of methane, since it's supposed to be more potent than CO2.
It is a question that is, hotly debated. How much methane and then actually CO2 could escape the frozen tundra? Pardon?
You have to closer to the microphone.
So there are actually quite a few numbers, but I don't think there is, to this point, there has been, anybody has come up with a good estimate of both the methane flux and the CO2 flux. If you take the extreme values, there will be a significant impact on the global budget. On the other hand, there are quite a few people who say these estimates are too high.
The microphone doesn't seem to work, or in the back they can. You get closer?
I cannot get closer. I have to bite into it if I get closer.
Oh, is this maybe working? Maybe?
I guess I reached the end. Just to summarize that quickly, the estimates are simply not accurate. On the high end, it would be a significant impact, but there are a lot of estimates that would not be that significant.
Okay, next question. The lady in the back.
Hi, this is also for Mr. Schlosser. I just wanted to check, because you're racing through the slides at the end. I think you said that the decrease in aerosols had also decreased the chance of cyclones. Did I get that right or wrong?
Increased. It increased them.
The decrease of aerosols increased the chance?
Increased the chance of cyclones occurring in the North Atlantic.
How does that work?
It's pretty much the you can, if you have quite a few aerosols, they are shielding radiation and heat coming in, so you can store more heat if you are taking some of the aerosols that are deflecting heat back into space away from that area. So you pretty much, when you are lacking the shielding effect from the aerosols, more energy, solar energy, penetrates and can be stored, and thereby you feed the hurricanes by warmer sea surface temperatures.
Yep.
In the latest report, was the comment made that there's less confidence that drought is an issue due to climate change?
Yes.
Could you comment on that? Because some people would be surprised by that. I mean, didn't Lovelock say that the biggest danger from climate change would be drought and low crop yields? And I guess the other presentation says that it's temperature and drought and water doesn't matter, right? But would you like to comment on that somewhat?
Peter again. Yeah.
Well, let's go to Wolfram on the drought and crop yield, because that was part of the question. Then we can go back to.
So again, I think droughts are also caused by higher temperature. So I think it's just a bigger driver for a drought, the temperature increase, than the actual precipitation change.
But the report's backing off that. That's why I'm really surprised.
Yes.
The place where the report backed off was it attributing current drought patterns to climate change. And it softened a little bit as far as the future, but I think the statement is in there that if you look at the future, that regional drought there's a moderate level of confidence that regional drought will increase in certain areas, that is. I don't have the report with me. But the big change was that we can't assign a probability that current drought was caused by the buildup of the greenhouse gases.
12-year droughts in so many different places.
There's a lot of historical variability.
Yes. I come. All right.
Well, one is my interest in it feels like a corporate projection. It goes no more than 5 years. Now we've got a human race projection, and it goes no more than like 15, 20, 30 years. What happens in 100, 200, 300 years when we've surpassed that ideal point where plants can easily what's the idea? We're stuck with this for a long time to come. It's going to continue to gain for a long time. And so what would you say that, we can easily go back 1,000 years. It was a time when, Christendom was beginning to either, come the very first seeds of its demise. What would you say 1,000 years from now would look like?
So,
both physical and then cultural.
To whom you want to address the question?
It can be to anybody.
Anybody.
Covers them.
So there's a lot of uncertainty out there, probably in 1,000 years, but
economics want to chip in on this.
Well, so it's a kind of an interesting question because actually in the things like the social cost of carbon analysis, you actually do have to go run economic projections out 300 years. And, that's impossible, basically. Anything could happen in a 300-year time span. But the physics of the problem is easier. If you specify, as in the representative concentration pathways, what the emissions are, then you can project with moderate degree of confidence what the physical effects, particularly on global mean temperature, are going to be. So I actually splashed up on the screen very quickly 300-year projections of temperature associated with different representative concentration pathways. In the, I think, fairly unlikely event that we just continued on RCP 8.5 and there was no human response whatsoever to temperatures yielding effects of the sort that I was showing where you start rendering parts of the world uninhabitable, then you get to a situation where by the second half of the 22nd century, temperatures start getting up into this relatively absurd range, 10 to 20 degrees Fahrenheit of warming beyond today. Understanding what's actually going to happen requires predictive social science, which basically doesn't exist.
Anybody else?
Just one point on that. If you even take a moderate scenario, if we are not turning to almost negative emissions, by recapturing some of the CO2, and you let the CO2 level go more or less where it is now, or not doing much about it, and the temperature rise is what has been projected, you are seeing things like, the Greenland ice sheet can be actually melted on time scales that you mentioned. Several hundred years, maybe 1,000 years. If you would remove the ice from Greenland, you would have 7 meters, 20 feet roughly, of sea level rise. That would really change the landscape, literally. I mean, if you just look at the coastal infrastructure, that, we were talking about a few feet, now you are talking about many meters. At that point, you also have to start to worry about Antarctica, which holds many more meters of sea level rise, let's say 65 or so. And these are things that, if you want to project out and you want to take the uncertainty into account that comes with it, because the further out we go, that's why we actually stop usually at about 50 to 100 years out. If you keep in mind that the uncertainty gets larger, you can sort of come up with some scenarios of how bad things could actually get, just from a physical perspective. And that, of course, ripples into the impacts, into socio-economic systems and so on and so forth.
Well, technically, I believe that the potential possibility there for large parts of the Antarctic slide right into the ocean and causing massive raises in the sea level of like 10 feet or
Greenland would be actually 7 meters, 20 feet, and Antarctica, depending on how much you take, it can be up to whatever, 60, 70 meters.
So my question here is this: so isn't our system completely wrong? And how come we speak so little about the problems with our system, the amount of calories that we, even us who know so much better, consume, and we don't change? So the question comes in, do we really have clear answers as to what to do? Because every scenario that I'm seeing, or every discussion about it, assumes that we're just going to barrel on through and efficiency is going to somehow save our ass. And that's nowhere near going to happen.
Can we still go on with some of
that's
our questions? Okay, maybe they can answer implicitly a little bit later, but there have so many friends who want to bounce this question here, and then we go to the back.
This is a very mundane question, simple. What happened in the Philippines last week and what happened in the Midwest, Chicago and other places today, are they directly attributable to climate change? If so, will we be able to convince Dick Cheney and his ilk about that it is directly attributable?
Maybe we can have 2-3 questions and then you can answer. Maybe that's more economic here. No, in the back and here's the lady. So just
in terms of messaging and reaching the general public, I'd like to suggest we start speaking about carbon pollution instead of carbon emissions, because people understand that pollution is negative and environmentally destructive, whereas emissions is just very value neutral. Just one suggestion I'd like to make. Secondly, in terms of the climate change talks now, do you see any possibility for an agreement? And third, to any of you, what do you see as the key policy measures that we must advocate for?
could you pass on to your neighbor maybe, then we come back here.
Yes. My question is for Professor Schlenker. I'm trying to connect the dots with 2 articles that came up in the Journal of Economic Literature, one from Stern and one from Pindwick, and they were saying that scientific models just underestimate the risk of a rising temperature above 3 degrees C, and actually their projections were really apocalyptic. It was, a loss of 50% of GDP by 2100 or something like this. I just would like to know if you concur with that, and what's, again, I'm just trying to connect the dots with economic modeling. And
maybe one.
Thank you all very much. One question, I have 2 questions. One,
quick question,
is all of this being put into the talks going on in Poland? All this information. And the second question is there a study that says if we have 20% renewable energy, we can reduce it by this much? If we have 30% renewable energy generation globally, we can reduce it by this much. In other words, a study that gives us hope. A factual database study that shows the improvement that we can make in preventing this disaster by percentages of renewable energy installed.
Okay.
Thank you.
Can we have now a quick response first to the 3 or 4 questions? I come back to you in a second.
Thanks. So a few points. I guess key policy parameters. I actually do believe in markets, and I do believe if you price carbon correctly, like with the carbon tax or with a tradable permit system, that it could go a long way in giving people incentives to innovate. I think we just need to shift the debate. So we were this, in the 1970s, you heard like limits to growth, and all the people were worried about is that we're going to run out of resources. I think the paradigm now is, the big problem is if we actually use all those resources that we have. And once you realize that, I think that there are possible market solutions that would go a long way. I mean, it's even now if gas prices go up, people switch to more efficient cars. I do believe there's something to be said there. Obviously, all the oil companies who would lose tremendously because their scarcity rents would completely collapse are vehemently against this, so it's tricky to implement that. I agree. Well, I'm not a climate scientist, but there are papers like by Weitzman too that basically says it's all in the fat tails. I mean, that is, I completely agree with that, because if the function is non-linear, then the average outcome is not the outcome evaluated at the average climate. It's basically you have to integrate over the whole possibility. So if there are possibilities that you have extremes that can limit things, I do believe it has huge potential negative. I sometimes feel people misunderstand the most basic economic principle where we talk about consumer surplus. So Adam Smith talked about, you know, the paradox of value, where diamonds are expensive even though they're not really necessary to survive, while water is cheap even though you need it to drink. But it all has to do with scarcity, right? So sometimes you hear economists say that, oh, it's only 2 to 3% of GDP, why should I care? But it's 2 to 3% of GDP because the value currently is low because it's priced very little. But we all need to eat. There's tremendous amount of consumer surplus, and that's really welfare, what we should care about in the food market, for example. And we've seen that prices have been tripling between 2005 and 2008. So there's definitely the potential for quite significant damages, I think.
Yeah.
Okay. So I guess a couple of comments, starting with the first question on hurricanes and tornadoes. I'm not aware of much good research on the relationship between tornadoes and climate change. On hurricanes, there's the work in the North Atlantic cyclones that Peter talked about. Attribution work, so work trying to attribute changes in cyclones and other basins is very ambiguous at the moment. Going forward, there's a general consensus that we'll see more intense storms and sort of lack of clarity in the literature on whether you will see more or less storms overall. Whether, you know, with Sandy, as I point out, the thing we can say most clearly is that the amount of flooding was affected by sea level rise that's linked to climate change. It was probably, the intensity of the storm was probably also affected by the unusually warm waters off the coast of the U.S. during that time period. And then there is some very, very heavily debated work about whether the direction the storm took was related to blocking patterns over the Arctic that were associated with low Arctic sea ice. I guess a comment on the UN Framework Convention talks in Warsaw. I think this is international climate policy is long and complicated and slow. I think that the idea that a lot of people came into Copenhagen with that you would sort of get some sort of global Kyoto agreement to agree on sort of caps and targets for specific groups of countries. I think that seems very unlikely. The U.S. is probably not going to agree to something unless China agrees to a more or less reciprocal thing. China is, after all, nearing double the U.S. in CO2 emissions. It's not quite there, but the changes over the last few years have been quite remarkable. And China is doing stuff, but my impression is that they're uncomfortable, committing to strong international agreements, even though they may be actually willing to do significantly more than they're willing to put their commitments onto, as though they actually believe that they should be signing on to things only if they're sure they're going to do it. I think some of the U.S. actually position may not be that different. I think you're unlikely to see the U.S. signing on to very specific carbon targets, but you will probably see the U.S. supporting collaborative actions, doing things to reduce emissions. So there are pathways other than the UN Framework Convention as well, in which the U.S. is trying to do that, things like the clean energy ministerial process, trying to get countries to actually agree to do specific things to advance sort of regulatory policy and technology cooperation. And I would just agree with the comment on the damage estimates above 3 degrees C. There's basically no real substantive research to speak of. And one last comment, a question on renewable energy and integrated assessment, renewable energy, and that's basically a large part of what the field of integrated assessment modeling does. Is, let's say you have a specific climate goal, what sort of energy system transformations do you need to be consistent with that? So there's the field is called integrated assessment modeling. So you can look at studies from places like Pacific Northwest National Lab or MIT, and there's a body of work on this. And so actually the representative concentration pathways that you saw, there are studies that will show that will show sort of what sorts of energy system transformations would be consistent with each of those pathways.
Peter, you want some?
Just two quick points. There is actually no statistically significant correlation between the change in temperature that we see and the frequency of cyclones over the past 4 decades or so. There is, as has been mentioned by Bob, there is the suspicion, and that's fairly straightforward. If you put more energy into the system, the intensity of the cyclones can increase. But it's still sort of in its infancy to work out this relationship. On the question of renewable energy, there are actually only, if you look at the way or the possibility for us to produce enough energy for the world population at the rate that it is demanded, there are only 3 sources that can do that. And some of them have serious issues. There is fossil fuel, and there is nuclear, and we saw how nuclear was actually hit by Fukushima and other things, but Fukushima really sort of did it in for the time being. And the third one is solar. And the question, pardon?
Wind as well.
Wind can do some, but wind is limited. If you wanted to take most of the energy that we are taking now out of wind, you actually can slow down the atmosphere. So if you look ahead and if you look at how many terawatts of energy globally we are using, and you project how much we might use, the ones that really can be scaled are the 3 that I mentioned. The others should be applied to the extent that we can, and that goes for wind and for tidal energy and for whatever you can do. But in my view, the best hope that we have to make a real dent is to develop the solar energy. But it will come with another set of issues.
We could still one round of question. Here's was one quick question.
Yes,
A quick question, please, and then on the right here. Yeah. Sorry, but maybe
My
the second
question,
one.
with all due respect to Professor Schlosser, I was quite stunned at a statistic that you gave that the parts per million of carbon in the atmosphere is projected to hit 560, at which point we will only see a 2 degrees centigrade warming. I've never heard that number before. I always heard the number was somewhere between 3 and 400 parts per million would take us to a 2 degrees centigrade warming. And another question is that I was wondering if the data is not in your estimation on methane emissions and whether they do have a significant impact. When can we see that study to corroborate or to disprove the Cornell study? Thank you.
There here on the right, there's some 2-3 questions. Ed?
Okay.
Yeah, okay.
I'm curious about one possibility that I remember actually talking about a few years ago, and that is that if global warming is sufficient to create a strong melting flow in the Arctic, and particularly around Greenland, this might cause the flow upward from the Caribbean to falter and perhaps completely dissipate. And that would create not global warming, but local cooling in Europe. And if I'm not mistaken, it would be a fairly large effect. Could you say anything about the likelihood?
Can you give it to your neighbor behind you? Behind.
Tony Collin from the University of East Anglia, currently at the Earth Institute, working on water and climate change. Just to say that I'm hoping this is being recorded and put out maybe on C-SPAN. I think the representation of AR5 has been excellent, so accurate, so detailed, and I'm glad it's been given with no gloss, which is extremely important. You haven't mentioned the Sustainable Development Solutions Network, the work it's doing going forward at the EI, and work on renewable energy. We have the Open Working Group of the UN, which is next January, and the meeting of the UN next year, which is going to be dealing with climate change as part of the Millennium Development Goals moving into Sustainable Development Goals. So is this being recorded, and could perhaps Peter mention and talk about the Sustainable Development Solutions Network? And a question quickly for Bob. You mentioned on your very first slide the emphasis on population and on affluence being two of the key drivers of CO2 emissions. Would you like to comment whether it would be helpful if we could perhaps stabilize the Earth population on one side and also stabilize the amount of consumption which we are consuming, not just of energy, but of stuff?
Here you go, briefly.
Okay. Economists are using your results to feed into, I guess, growth models to project GDP projections and other projections over many decades. And I wanted to ask, I think using the Kaya identity, and I wanted to ask, in light of these new results, are these models, should they be, do they need to be adjusted, especially with these possible nonlinear effects that we know so little about?
Is one question more that we can take? No, wait, if here's one question more, then this person. Quick question.
Yes, quick question. Secretary Moniz spoke at Columbia a few months ago about this, and he mentioned that 9 out of 10 of the deadliest hurricanes in the southeast region of the U.S. have been in the last 10 years. That seems like a startling statistic. I'm just wondering if there's evidence to back that up, or is that just due to poor measurements in the past? And then just a quick question about China, since it was brought up. I know that we've been able to decrease CO2 emissions in the U.S. We're about halfway there. I think the Obama administration is trying to decrease it by 70%. And when he said it was largely due to coal, switching from coal to other natural gases. But is China doing anything similar? Are they kind of on a pathway to putting forth policies that will actually make a difference in the environment? Thank you.
Michael, do you had some? No. Okay, I think then we give the speakers a chance to reply to 4 or 5 questions.
Okay, just very quickly. When I talked about methane, I didn't talk about the global methane emission. I just talked about the uncertainty of the amount that will be released through the thawing permafrost in the Arctic. So that is uncertain. There is much more certainty in the rest of the globe. Then, with respect to the slowing down of what is typically called the conveyor belt or the marginal overturning circulation in the Atlantic, if we use our measurements, we don't see any effect yet at this point. We cannot measure it yet. If we are using models and we project out, what we get as a best estimate is that the warming over the North Atlantic, where this would play out, would be moderated, but it would not counterbalance the warming that we have due to the increase of greenhouse gases. So there would be, and you actually see it in the maps. If you look over the North Atlantic, if you look at the projections of future temperatures, you see a little area that heats up less, but it's not cooling. And then with respect to SDSN, the Sustainable Development Solutions Network, it is of course one of several means that will contribute to formulate the so-called Sustainable Development Goals, which will follow the Millennium Development Goals. It is a partnership between many institutions. The Secretariat is at the Earth Institute, and its goal is to figure out how we actually can apply means to go onto a sustainable pathway into the future, including going towards a carbon-free energy system, but also others in terms of poverty reduction, etc. And it is meant to bring academia into the discussion of what is possible, including negative emissions, but in the end, the decisions will be made on a political level. And this will feed into it, but if it will actually penetrate, that's something we have to see.
A few quick responses. So there's a question about climate sensitivity. So there's two important concepts there. So there's the climate sensitivity. So what would happen if we say froze CO2 concentrations at 450 ppm and kept them at that level? For a CO2 doubling for 560 parts per million, our best estimate is that would lead to 3 degrees of warming. But that's a long-term response. If you actually the point I wanted to make earlier about the long-term future, most model results suggest that the interplay between heat storage in the ocean and carbon storage in the ocean is such that if you were to stop emissions today, temperature would stop going up, and it also wouldn't go down much for a very long time. So that's where things like the 2-degree level for that middle, by 2100, for that middle pathway is related to these delays in the system. 4.5. For RCP 4.5. I just mentioned on the AMOC slowdown, another significant effect of that would be sea level rise. So you can get about an extra foot of sea level rise off the east coast of the U.S. from AMOC slowdown, from the conveyor belt slowdown predicted in this century. Population and affluence. And one of the things I'm sorry about for this assessment report is that the scenario process, the shared socio-economic pathways, weren't further along by the time the report was released. If you look at those SSPs, which are, there are some papers out now about, but I think they mostly weren't out in time for some of the later volumes of the report. The SSP with the highest emissions, which is actually higher than RCP 8.5, it's about 9.5 watts per meter squared by 2100, is one with relatively low population growth, where population declines back to about 7 billion by 2100, but sort of conventional development, so fossil fuel intensive development, and GDP per capita going up rapidly. So this is called the conventional development pathway, and it ends up with GDP per capita around $100,000 by the end of the century. And in that scenario, that's how you get to the highest emission scenario. On the integrated assessment models, yes, I think the damages need to be updated to take into account research that's been done in the last 15 years.
Yeah, I mean, so there are some that look at the tails more. So Weitzman has a paper on fat tails that sort of incorporates it. Some others, like Pindyke, are more skeptical, but I think it's being undertaken. I wanted to say about the hurricanes. I don't know about the physical side of whether they gotten that much worse, but one other thing that contributed to the lot of damages too is that we've seen people move actually in the way of where the hurricanes hit. So we had a lot of land use change at the same time, which makes the population was acceptable. And one particular bad thing here is the subsidized flood insurance that the government sometimes is giving out, which encourages people to live in areas where you might not necessarily want to live. About China, I think China's point is often, I mean, if you look at the cumulative emissions of the developed world and what they've on a per capita basis emitted, they're just very low, even though they're right now the biggest emitter. There's all those clean development mechanisms from trying to get them to agree that, the developed world can get credit for sharing technology, other things. I've heard a rumor, and I don't know whether this is true, that they had a plan for a carbon tax in their next 5-year plan, but it doesn't say at what level it would be. But at least they're toying with the idea that they might have it. I'm not sure it's actually going to happen.
I think we have to stop now, and I want to thank the patience of the audience to stay that long. It's after 8 now, after more than 2 hours, and the patience of the live stream audience, and thank particularly the SIPA and the speakers to stay with us for more than 2 hours, and particularly Wolfram is probably now pretty exhausted after the long trip. But anyways, it was a wonderful discussion, and we will continue in the spring with another big event on climate change. We don't have yet an exact topic, so you may send us some topic to Twitter or other means that we can maybe organize the next event around this. So thank you very much for coming.